Free expansion of a gas. Figure shows schematically an experimental arrangement used by Joule to study how the internal energy of a gas depends on its volume. Consider the system A consisting of the closed container subdivided by a partition and containing a gas in one side only. The experiment consists simply in opening the valve and allowing the gas to come to equilibrium throughout the entire container. Suppose that the thermometer indicates that the temperature of the water remains unchanged in this process. What is the work done on system A? The container walls are rigid and do not move. Okay, so since the container walls do not move, we don't have any work done. So we should note that the container walls do not move. Therefore, the work done on system A, which is minus P bar dV, because the volume is not changing, is going to be 0. And furthermore, if you concentrate on the gas only, there is no external force acting on the gas molecules. We simply open up this valve and the gas molecules fill the full container. So there is no external force acting. Therefore, the work done on the gas is 0. So W is 0. Now let's look at part B. What is the heat absorbed by A in this process? Now, the thermometer reading doesn't change, so the whole system is at equilibrium. So it's quite clear that system A has a constant temperature. And remember that thermal energy, kT, is an indicator of the mean energy above the ground state energy per degree of freedom. So if this is a constant, we find that the mean energy of the system should not be changing. So delta E bar should be equal to 0. And from the first law of thermodynamics, delta E bar, which is the heat absorbed plus work done on the system, is 0, and with W equals to 0 also implies the heat absorbed by the system is 0. So the fact that the work done on the system is 0 with no force being applied makes this a free process, and the fact that the heat exchange with the environment is 0, it makes it an adiabatic process. Now in part C, what is the change in the internal energy of A in this process? I just argued that kT is proportional to mean energy above the ground state energy per degree of freedom. This is a constant, therefore delta E bar is 0. Besides, we could also argue that there is no heat exchange, because if there was heat exchange, I would observe a temperature change in the temperature of the water that I'm measuring. So you can also say that Q is equal to 0 because the thermometer indicates no change in temperature. So that's an alternative way to argue about this. Now in part D of the problem, Since the temperature of the gas is unchanged, what conclusion does experiment allow one to draw about the dependence of the internal energy of the gas on its volume at a fixed temperature? Now we are observing that the derivative of the mean energy with respect to volume at constant temperature is zero. So that's the conclusion of this experiment. And since delta V in the process is non-zero, but the change in the internal energy is zero, we can conclude that the mean internal energy at constant temperature is independent of the volume. So this is the conclusion we can draw from this experiment. And once again, from these observations, since the walls do not move and there is no force acting on these gas molecules, it's a free expansion process. Since the temperature of the water doesn't change, there is no heat exchange with the gas and the water, we have Q is equal to zero, therefore it's an adiabatic process. So I recognize this process as adiabatic free expansion of a gas. And because the thermal energy is an indicator of mean energy above the ground state energy per degree of freedom, and that doesn't change, so the delta E bar is zero. And even though there is a change in volume, there is no change in the mean energy at constant temperature, indicates that E bar at constant temperature is independent of the volume of the container V.